Hey everyone, welcome back to another recorded session of our SD-WAN training. Hope you all are doing good. In the previous session, we discussed about the very introductory course outline of the course that we're gonna cover in this self-paced recorded sessions of Cisco or Viptela SD-WAN. And in this session, we're gonna get started with one of the first topics, that is introduction to SDN. And we're going to discuss about how it works. So let's dive deeper into it so that we can understand the differences between the traditional networks as well as the software-defined network, and how the SD-WAN infrastructure or architecture is based on SDN. So since we're going to talk about introduction to SDN, that is software-defined networking. So SDN is not something new. I always speak about it in one of our early sessions whenever I have any online or on-site training. I do mention that in most of our automation-based trainings, be it DevNet, be it SD-WAN, be it any other SDN focused training. I always mention that in our sessions that SDN is not something that is new. SDN has been there in the market for almost around a decade now. It is just that it hasn't been very popular. If I give you a brief history about how SDN came into being, in around 2013 or 14, there were two solutions mostly that Cisco came out with. Cisco had something called Epic EM, you might be aware about that, and Cisco had Epic DC. So application policy infrastructure controller enterprise module and application policy infrastructure control data center module. Both of these particular solutions were there to manage something about the LAN and WAN, and Epic DC comes up where we had data center networking that can be managed. It had other products also, something like Prime Infra. Then it also came up with iWAN, Intelligent WAN, or various other things. But these two were the majority of them which were supposed to be popular. After that, the Epic EM got distributed in two parts. So Cisco created something called SD-WAN out of it and SD access out of it. And out of Epic DC, they created ACI, which officially uses a controller called Epic. The SD access uses a controller called DNAC, DNS Center, and SD-WAN uses a controller called vManager. Right? So all of these particular solutions are SDN based solutions which are becoming very popular nowadays in the industry, out of which we're going to talk about the SD-WAN. But before getting to know about that, let's first talk about SDN. So like I said, SDN have a very long history to go, and it's been there in the market, and now it's been very popular. But before understanding SDN, you first need to have a solid grasp on how does the traditional network function. So in traditional networks, we use various devices in our networks, be it the routers, be it switches, be it firewall, be it load balancers. Then we have IDS, we use IPS in our network, and certain other devices. And most of these particular devices are manufactured by top vendors. That includes Cisco, right? That includes Juniper, that includes Ciena, that includes Huawei, then we have Checkpoint, we have Palo Alto, we have F5, we have FortiGate, and certain other Arista, Nokia, and whatnot. All of these networking or all of these networking giant companies who manufactures these devices do provide one or the other way to manage your device. So if we have, let's say, a router, and that router will be having various ports on the front end, it might be having all of these gig Ethernet ports or Ethernet ports or fast Ethernet ports or 10 gig Ethernet ports, and on the back end it will have some console port, it will have some auxiliary port or so. So generally there are two ways of how a device can be managed. One is you can manage the device by using local connections, and you can manage the connections by using you can manage the device by using remote connections. If you want to manage the device by using the local connection, then you generally get connected with that particular device, maybe by using an admin machine. And on the admin machine, it can be, let's say, a Windows device, and that machine will be installed with some software like Putty. So we will be accessing the device and the CLI of that particular device from this admin machine and send config commands onto the device. When we send these config commands onto the device will be configured according to admin's expectations, and then we'll start forwarding traffic here and there according to the instructions that have been passed onto the device. That's one way of managing it. Other way of managing these devices, by using either of the port, you can expose that device out onto the internet, and maybe there can be a remote user who's sitting there, who's also using softwares like Putty, and you can connect with the device by using remote management protocol like SSH, Telnet, or maybe HTTP nowadays. So this way you can manage that device. Now earlier, back in the days, whenever an organization would create any networking infrastructure, then they would mostly purchase devices of same vendor. They would purchase their routers and switches and firewalls, which are manufactured of same vendor. And then they would also hire people who knows how to work and configure these devices. But later, when the trend started to implement multi-vendor network infrastructure, then there was no commitments, right? Your organization would purchase some routers from Cisco, then it would purchase some other devices, let's say switches from Huawei or Dell or some other vendors. And then they would also require people who knows how to configure multi-vendor devices. You would be looking for people who knows how to configure a router that's manufactured by Cisco, another router that's manufactured by Juniper, maybe a firewall manufactured by Cisco and Juniper and Checkpoint and FortiGate, right? Certain things. Then it would become hard for network engineers to remember all these commands that they need to use in order to configure these devices. So then organizations, these organizations who would create the devices started to come up with GUI solutions. So like Cisco came out with a very popular device called ASAV, right? So that ASAV could be configured both ways. Either you can configure it the CLI way or the GUI way. On the same admin machine, if you want to configure the CLI way, you would use a software like Putty. And if you want to configure the GUI way, you will use ASDM, Application Security Device Manager, a special GUI utility which was designed for ASA firewalls. And by using ASA, your network engineer would be able to configure that device without actually worrying about mugging up the commands that he or she needs to use there. Without remembering the command, you would end up configuring the ASA completely. So that was one approach. And then other industries or other vendors also did come up with these solutions that providing GUI and CLIs, so that network engineers can configure devices without really worrying too much about remembering the CLI commands. But yeah, this was one approach in terms of optimizing how network operations are handled back in the days. And then there is another aspect towards how the network devices inside of themselves function. Let's say you have a topology. I'd give you a topology, for example. We have a router 1, and then that router 1 is connected to router number 2, and then router 1 also has a switch and then some PCs connected to it. Router 2 again would be having a local area network. Router 1 uses a network like 192.168.1.0/24, and router 2 uses 192.168.2.0/24, right? And then we have 192.168.3.0/24, and we connect these networks by implementing, let's say, static routing. Once we have that static routing implemented, let's say the communication needs to be done between 1.0 and 2.0. So how would the traffic flow? The traffic, for example, originating from this PC will go to the gateway first, that is router 1, and then it will jump up to router 2, and then from router 2 it will go to the destination device that might be here. But while the communication is going from this PC to the gateway, what does the gateway do? The gateway is going to perform lookup into the routing table, checking if it knows about any particular route like the source route and the destination route. And since this is the source route and this is the destination route, what's the next stop for that particular route? Where does it needs to forward the traffic, the received traffic, in order to meet the destination? Then it would figure out that the next stop of it is possibly 192.168.3.2, which assuming is this interface. Then what is the ARP address, or by using the ARP, what is the MAC address of that particular IP address? That would be figured out. Once all of these resolutions are done, then your traffic will be sent to R2. R2 will again perform lookup into the routing table, that does it know about the source network and does it know about the destination network. If it's checked and checked, then the traffic will be forwarded down, and similarly the reverse traffic will be forwarded. So when you think about that, there are a lot of things that goes on into the network, right? Be it calculating the best path for reaching out to the destination. Like for the same scenario, if you had another router in place, R3, then the router 1 can forward traffic this way or this way. So internally, your router needs to decide that where does it needs to forward the traffic, select the best path, right? Then if it has other things to do also, for example, number one thing that it performs is best path calculation. Then it also needs to perform ARP for resolving the MAC addresses. Then it also needs to perform TTL change, that every time your traffic crosses a hop, a TTL value, time to leave value, needs to be decremented. Post that, it also needs to perform cyclic redundancy check. It also needs to take care of other traffic that's going on. If you have a layer 2 device, then your spanning tree protocol needs to function, your VLANs needs to be intact, right? Your trunk traffic needs to be negotiated always. Lots of things happens onto your network devices. And to handle all these jobs, it's not just about forwarding traffic, right? To handle all these jobs, there are some planes which are available. So every plane has number one called management plane. Then it has control plane. And then it has data plane. The user usually sits over here and interacts with the device by either using CLI or GUI. So when we say that the user is interacting with the network device using CLI or GUI, user is doing nothing but speaking with management plane of that particular device. Once the user instructs the management plane that, let's say, OSPF configuration needs to be done, or let's say STP configuration needs to be done, or so on. Then the management plane takes inputs from the device, right? And after that, it instructs the control plane that, hey, control plane, I've got this configuration from the user. Can you please apply it on your processor? Because control plane is an element that closely works with CPU. Or you can say control plane is nothing but CPU. So management plane instructs the control plane about the necessary configuration that needs to be done. And post that, the control plane is also going to notify data plane about the best path calculations on all of the decisions that it had made, because data plane works with the line cards, or you can also call it as interfaces. And that's how a device is made up of. If I give you a very logical overview of it, think of it this way. You have a device, and let's say this is your router 1. That router 1 has a small component called management plane, and you sitting over here speaking with management plane. The management plane then speaks to the control plane, and let's say it asks you to configure OSPF, to configure EIGRP, and let's say there is also some static routes that are working up. So what will OSPF do? In OSPF, it will form the neighbor table, right? It will also form the link state database table and so on. The EIGRP will also do topology table calculation and the neighbor table calculation. Static do not really work with any tables though. But then after that, there is something called a routing information base. So the best path from these LSDV will go into routing table. From the topology table, it will go to routing table. And from static, it will directly go into routing table. Right? So the best path will be calculated. Then there will also be ARP negotiation. So ARP also comes into picture for finding out the MAC addresses of the next hop and so on. All that happens in the control plane. And then there is another element, which is then data plane, which maintains something called forwarding information base. So all the interfaces of the device, let's say over here, for example, this is G0/0, this is G0/1, this is G0/2, G0/3, and G0/4. So if the traffic comes up here, since the information to the forwarding information base will be given from routing information base itself, right? So management plane cannot directly talk with forwarding table or data plane. Neither you can directly talk to control plane, or you cannot also talk to forwarding or data plane. You can only speak to control management plane speak to control plane, control can speak to data plane. It's the hierarchy that every device needs to follow. And once they follow that, the information will be updated. So whenever there is any traffic that comes up into the data plane or onto the line interface, then the traffic gets across the forwarding information base, then gets decided on which interface it needs to go, maybe this interface, and the traffic will be forwarded. If you implement any network address translation services, if you implement any access control list, that traffic will be filtered directly from here, from the forwarding information base. So this is how the architecture of a specific device works. In that case, if you assume, since all of these elements are available on all devices, if you say management plane, control plane, and data plane, these elements are available on R1, on R2, on switch 1, on switch 2, everywhere. You can see that how much of overhead do we create on our devices so that they can be managed and they can work in the proper way. That's about how the traditional network works. But what all are the limitations then? So let's speak about the limitations now. Limitations of traditional networking. So speaking about the limitations of traditional network. Now let's talk about a scenario. Let's say we have an ISP. Wow, good approach. So that ISP is providing us the services to connect our sites across the geography. So we have one site hosted in Dubai. We have a WAN edge router. That WAN edge router is connected to internal devices and maybe some networks inside. Similarly, we have another site that is in London, and we have a WAN edge router and similar kind of architecture. And then we also have a headquarter in maybe Singapore, like this way, or better, right? And we have a server there. That server has several virtual machines installed, virtual machine number 1, number 2, and number 3. These virtual machines are nothing but business applications. Right? Can be enterprise resources, can be customer relationship management, can be any other tools that the employees which are sitting in Dubai and London office needs to access on their daily basis, because they need to do their job by accessing these applications. And let's say that we have then we need to put that particular server in network so that the sites, the Dubai side and London side, can access this particular thing. So we might put up redundancy in our network, in our headquarter, having, let's say, router 1 and let's say router 2, both of them connected to the transport. Then we might have some internal security. So we have firewalls monitoring all the traffic. To be able to aggregate the traffic, we have layer 3 switches down. Then to be able to distribute the traffic, we have layer 2, and then that connection goes to the server. In terms of assuring the redundancy, we also have implemented mesh connectivity between them, so that wherever the traffic goes, by using any way, it goes to the destination. So you can divide it this way, that this is the core of your network, this is the distribution or aggregation, and the remaining is access. Right? 3-layer hierarchical model, you can say. To implement that, we might need to implement, let's say, BGP, then OSPF needs to be there, access control list, network address translation, firewalling, spanning tree protocol, VLANs, inter-VLAN routing, subnetting, right, trunking, and ether channel, HSRP, whatnot. Lots of the configuration needs to be done on these devices as well as on these devices and these devices to make this function. And while configuring that, remember that your management plane, your control plane, and your data plane, these components are individually available on all the devices. So the admin needs to connect these devices and configure them with the required parameters, right? So that's kind of a limitation. The network is slow. The network is manually configured. The network is error prone and very lazy in terms of being managed. All of these parameters comes into picture when we speak about operations. I'm not saying that BGP will work slow. I'm not saying that OSPF will work slow. No, that's not the concern. The concern is, how do you manage that network? For example, let's say there is a requirement that 3 new virtual machines needs to be pushed over here, 4, 5, 6, and these are kind of new virtual machines or new applications that the organization have decided to be deployed. So how does it work with that? In such scenario, it's easy for a virtual machine guy to implement the new virtual machines, but for a network engineer to make those particular virtual machines accessible, it will have to push a lot of configurations onto the device, right? They will have to manipulate the subnetting, they'll have to manipulate the BGP, they'll have to manipulate NAT, ACL, OSPF, and whatnot, HSRP, new VLANs, changing the firewall rules and everything. So in order to achieve that, what we do, we ask our admin, or the admin distributes that task to the team of network engineers, and then they do further configurations. But this cannot be done easily in the business hours, right? So the team might create a maintenance window in the night, and then they will deploy the changes onto the networking devices. That's the manual way of doing it. But like I said, it is the slower approach, it is a manual approach, it is an error-prone approach, and it is a lazy approach. Because according to Cisco itself, when Cisco created a survey, or they did a survey, they found out that around 80% of their customers are doing manual configurations. And out of them, around 60% of the tag tickets they get is just about misconfigurations, which means if their customers do not do misconfigurations at all, they will be reduced with the number of tag tickets that they get raised off. And that's a big thing. That's exactly where SDN comes into picture. What if there is a mediator who takes care of what configuration goes on to the device, verify that configuration, check the syntax of the configuration, check that it is compatible to be deployed in the current environment, right? And then when all these checks are implemented and taken care of, then push the configuration onto the devices. Otherwise, do not, right? So that's what SDN says. According to SDN, or software defined networking, you do not directly interact with the networking equipments. You have an admin machine. The admin machine talks to something called SDN controllers. The SDN controller might be hosted on the premises or on the cloud, doesn't matter, and it can be connected out to the ISP. Irrespective of what type of ISP do we have, we can have the commodity internet, we can have the private internet, or we can have cellular services like 3G and LTE, any of them. And then the ISP might be connected to various other sites. You have a London site, you have a Dubai site, you have a Singapore site that's actually headquarter, and then you have network equipments on the backend. These devices can be connected, right? So whenever this was not earlier there, the picture was just this, where each of these will have their own management plane, their control plane, and their data plane. But now these devices do just have data plane only, and their management plane is centralized, their control plane is centralized. So what do? You basically sit on the admin machine and you instruct what configuration needs to be done. Then there will be a two-way communication between the controller and the admin machine that, hey controller, I want to configure OSPF on my London office and on my Dubai office. The controller says, okay, give me the values, give me the parameters for that. The admin says, okay, that's my area ID, that's my process ID, and G0/0 and G0/1. These are the interfaces I want to be participating into the OSPF process, and send that. The controller says, okay, got it. Controller creates necessary configuration, right? It then checks that whether it's syntactically correct, functionally correct, programmatically correct, and it doesn't cause any harm in the current health of the network infrastructure. Once all the verifications are performed, then it will push the configuration to the London and Dubai site. So you interacted with the management plane. The management plane then interacted with the control plane to prepare the configuration, and control plane then push the configuration onto this devices, right? Instruct, prepare, and push. So all of this communication earlier was directly between the admin machine and the infrastructure devices, but now everything is via the controllers, and that's the SDN way. Doing this, you do not have to go on individual devices and push the configuration. You do not have to verify that the configuration is correct. If there is anything wrong, the controller will say that this is not a good value. Please use a correct value before your configuration being pushed. So there is no unnecessary downtime that causes by your misconfiguration. The configuration will not be attached by the device to the device, and it will save the downtime. It is faster because the controller will be able to push configuration on multiple devices in one go. So that's the benefits of it. Very high level of benefits that SDN provides you. And when we speak about the SD-WAN solution, then the SD-WAN solution allows you to manage WAN edge devices. Okay, only WAN edge devices of your fabric via an SDN controller. Okay, it doesn't allow you to manage the LAN devices of your sites. It will only manage you, the controller will only allow you to manage the WAN edge devices with the SD-WAN scenario. If you use SD access, then it will allow you to manage all the LAN devices as well. So there are different solutions. What we are speaking about is managing the WAN infrastructure. Another misconception that people have, that it will replace MPLS. Just a high level understanding or a one-liner that MPLS is not going to be replaced by SD-WAN. SD-WAN is a technology or a solution that has been brought into the industry to optimize ways of how your network is being managed, not how traffic forwarding is done. Okay, we'll speak about it more, but yeah, this is about how SDN works in terms of in comparison to the traditional network, how it overcomes some of the limitations of traditional network, and that's been all. So in this session, we first spoke about what's traditional network, how does it work, right? What all are the limitations of traditional networks? What's control plane, management plane, and data plane in general context? After understanding the limitations of it, how does SDN work, right? And how does it overcome the issues, the general issues that we face in traditional ways of managing our network infrastructure? I hope you understand the basics of software-defined networking. And then after having the knowledge of SDN, generic SDN, we will then, in the next video, moving ahead with how the fundamentals of SD-WAN. We will see how the components and architecture of SD-WAN, Cisco's SD-WAN, have been designed, and we'll be moving ahead with that with the further topics coming up. That's about this video. I hope you enjoy the content that we covered in this particular video, and I'll see you in the next one. Thank you so much for watching. Take care. Bye-bye.